Okay, guys, good afternoon. Ready for start. I hope that today we are using a very powered website and connection. I hope so. And I am recording this lecture, the first hour, and then share the screen. Okay. Okay, so I tried to conclude yesterday the first part of this model, the section airfoil model, the typical section, and this is the model, and we have introduced a couple of equations, and we are normalizing this equation, and we have found a set of undimensional parameters characterizing the fluid, and these parameters are the green underlined here are the offset, the undimensional offset, which is able to identify the elastic center here, and here we have. Let me. I'm sorry, but I have an emergency, COVID emergency to take decision. I have to answer to this call. I'm sorry. Mauro, ciao. Scusami, ma prima stavo in una conference call di un progetto e adesso sto facendo lezioni, però volevo parlarti un minuto. Volevo parlarti del primo anno e della possibilità nel primo anno di cosa che è stata chiesta oggi. Okay, I am very sorry, but I am going crazy in this period with this COVID emergency, and here I am for my best favorite job, which is teaching. Okay, so here are our. Can you hear me? Can you hear me? Yes. Yes.
Yes.
Okay, thank you, guys. So we have the following undimensional number. We have this number here representing the ratio between what happens in bending with respect to what happens in torsion in the natural frequency sense. So this is not properly the ratio between the first natural frequency of the system and the second natural frequency of the system. But this is the ratio between the first natural frequency of the system whenever the structural dynamic is decoupled, and the second one whenever the structural dynamics is uncoupled. Okay, and here we have the mass ratio, and this mass ratio is an easy interpretation of the mass of the solid structures with respect to the mass of the fluid structure in these cylinders. Okay, okay. And at the end, we have obtained these two equations of motion. Where is the equation? The first undimensional equation of motion is this here, with this undimensional term, this, and this. And at the end of this undimensionalizing process, we have our final equation, which are this equation here. Can you see this? Yes. And we started by this original dimensional system to this here undimensional system indicated here, and we have our mass matrix, our stiffness matrix, and we have here the load as undimensionalized through the presence of these two groups. Here in the denominator, we have divided by a force per unit length, and here we have a moment per unit length. In the left-hand side, if you do not consider this right-hand side term, you have the free response of your system, and you can study this free response by solving the problem of the natural frequency. So you should take the determinant of this two mass and stiffness matrix. In particular, we could do the following. You can, let me just give me a second. We can take this equation. Okay, here. And here we have this equation, and if you consider this part, here, you have something like mass matrix, undimensionalized mass matrix, as applied to the state variable system, derived 2 times with respect to undimensional time, plus a stiffness matrix like that applied to H and alpha. And in the free response analysis, you don't have this forcing term, you have 0. Therefore, if you perform on this system a model analysis, in the sense that if you consider this problem, determinant of k at minus omega square m equal to 0, you obtain 2 omega value, like omega 1 equal to blah blah blah, a number, and omega 2 blah blah blah, a number, which are in general different, absolutely different, by omega alpha and omega h, excuse me, and omega alpha. the second one, but they are probably related too. And what about the eigenvector? The eigenvector associated to these two frequency you should have are the eigenvector k minus omega, for example, omega 1 m, and you have the eigenvector zeta 1, and this eigenvector is a vector of two components. Is a vector, excuse me, of two components. For example, look, something like 1 and 0.3. And what does it mean? Can you see my hand? It means the following, that if you impose as a boundary condition 1 for h, the first degree of freedom is the plunge on heavy degree of freedom. So if you put 1 and 0.3 radiant as angle of attack and release, you should have something like hop, 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 with the frequency equal to omega 1. So this is demonstrate that you don't have, for this initial condition, a pure bending or a pure torsion, but you have a coupling. This is for omega 1, and you should have probably something for omega 2, but what you obtain probably should be the following. For the first case, for omega 1, you should have an eigenvector mainly dominated by h, so you should have h, first component, and 0.3 or 0.01 as a second component, representing the angle, alpha. And so you have something like that, hop, 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 mainly bending and a bit of torsion. For the second one, you should have a number, a vector, an eigenvector corresponding to omega 2, which should be zeta 2, and probably this zeta 2 should be something like 0.1 and minus 2, for example, which means that if you put 0.1 as plunge, hop, and minus 2, hop, for alpha, you should have something like hop, 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 hop. It is a torsion, but dominated by torsion, but it's not a pure torsion. And this should be probably the result when you have as parameter omega, capital omega, something like less than 1, with bending as first mode and torsion as second mode. Okay, so this is just to see what this equation is representing. I only want to introduce this model to you for showing you the capability of this simplified model. As very last point, I want to show you this L and M aerodynamic force. This force, by definition, are equal to EH, this, and E alpha, this other. And by definition, they are the projection of the pressure force onto the first shape, psi1, and this here, the projection of this on the second shape. Okay? And if you consider all the theory for unsteady potential flow, you will be able to identify, to write an analytic solution of this variable L and M as a function of plunge and pitch. In other words, I am giving you an analytic formula which relates the plunge and pitch, giving to you aerodynamic moment and aerodynamic lift. So this is exactly what the elasticity want to obtain. But see what is complicated this, okay? So you have second derivative of h. We don't know the details of this theory at the moment, but you can see that the lift is a quantity as unsteadiness less depending on h and alpha. How? And this is how. You have that this lift is equal to blah blah blah. We have a second derivative of h, second derivative of alpha, first derivative of alpha. So this part here, look, this part here is something similar to have an equivalent mass and damping for the aerodynamic, because you have coefficient multiplied by second derivative and coefficient multiplied by first derivative. So this is something similar to mass matrix, mass damping behavior. But we don't have only this. We have also this here. And this is a bit more complicated. And this is more complicated because we have, again, the pitch angle, the derivative of the pitch, the derivative of the plunge, but we have a very strange special function. And this is the special function. The special function here is a famous function also known as Theodorson function. This is a guy lived in the 13th, okay? Theodorson is, do you know the Glauert theory? Do you know this name, Glauert? Yes or no?
Yes.
Okay, so you know the Glauert theory, which is the two-dimensional theory for the airfoil, but steady case, steady. So the Theodorson function is just the extension of Glauert theory for the unsteady case. Okay, and this is the formula for lift and moment within the Theodorson theory, giving you time by time the lift and the moment as given by taking the derivative of this quantity. But we have also this quantity here. And if you take a book of elasticity and look for this formula as Theodorson lift function, you found this, but this is essentially wrong. This is wrong. Why it is wrong? This is wrong because the function C, also known as Theodorson function. So this is the Theodorson theory, and this is the Theodorson function. This Theodorson function is a complex function of K, and K is the reduced frequency, the Stroll number. So it's depending on frequency, omega, the physical frequency, omega, by the half chord divided by U infinite. So you have a frequency dependent quantity and within a time domain representation, which is absolutely wrong. The correct way for representing the Theodorson function is a frequency domain representation. So writing, instead of this second derivative or first derivative, the product between minus omega square and so on with respect to this quantity, okay? Multiplied by this complex function. So this representation of the lift is not correct, but it is known in many books. the correct formula is the formula obtained by considering, instead of h dot dot, for example, consider minus omega square by the Fourier transform of h, and so on, the other part. And here you have a product between this complex function and the Fourier transform of h dot plus b alpha dot plus u alpha. Okay, this should be the correct way for representing this. And in other words, I am saying to you that you could also using this formula, but only in the special case of harmonic motion. In that case, you can use also this time representation. And I am saying that this is a wrong frequency mixed time representation. And this was an old style representation of this quantity, which was originally introduced in the past century. Okay. However, what I didn't tell you how this formula is obtained. Okay, and one thing we could do is the following. Can we demonstrate that this formula as a limit case of steady motion is equivalent to the Glauert theory? This should be. And what means steady? Steady means time derivative equal to 0. So steady means don't consider this, not this, because we have time derivative. Do not consider this, where is it? And this, consider this. And what happened in the steady case? So this k is a frequency. So steady case means omega going to 0 or k going to 0. So if you evaluate this function in the steady case for k going to 0, you have that c is equal to 1. And therefore, in the steady case, we have that the lift in the steady case is equal to, steady means k equal to 0 and derivative equal to 0. We have the following: 2 pi rho ub, 2 pi rho ub, 2 rho pi ub, c is equal to 1, and then you have u again by alpha, u again by alpha. Okay, and so if you consider that this is, multiply this by 2, multiply this by 2 and divided by 2, and so you have a chord here, and if you consider 1/2 by 2, here you have the following. You have equal to 1/2 2 pi rho u infinite by alpha. So this is CL alpha, and this is the dynamic pressure. And so we have the standard steady formula for the lift considered in the Glauert theory. Okay, so we have introduced this unsteady model as a generalization of the Glauert model for representing our right-hand side in our aeroelastic equation for a section I4. Okay, I want to stop here for this model, and now please make a double bold-faced line. I want to go back to the general theory. Okay, what does it mean? The general theory actually is based on the representation of our elastic deformation of, for example, of a wing. Like this. This is the deformation, and this displacement field is represented by model coordinate. So we have the model shape function referred to generalized variable. And if we use this representation, we have for the motion in Laplace, please, and the fact that I am considering directly Laplace is close to what I said before as concerning this formula, which is correct if you see this in frequency or Laplace domain as product of this C function by the Laplace of Fourier transform of this parenthesis quantity. Okay. However, in Laplace domain, we have a model mass matrix because I have used the mode of vibration or the approximation by the finite element. And in Laplace domain, we have S squared plus K by the Laplace transform of the model coordinate equal to. So in the right hand side, I should have the aerodynamic force, but the Laplace transform of the aerodynamic force. But this quantity is supposed to be decomposed or expressed in this term. We have a dynamic pressure coefficient as typical in all the generalized aerodynamic force. Any kind of generalized force can be expressed considering the multiplicating factor given by 1/2 rho by u infinity to the power 2, which is the dynamic pressure. But after this constant quantity, elementary quantity, we have these three metrics like E4, E3, E2, and E1 matrix. We have a unique E matrix defined as the product of this partial matrix applied to the same model state space vector. Okay, excuse me, this is E1. And we have decomposed this aerodynamic operator. This aerodynamic operator E is a matrix depending on the Laplace variable, which is depending on the Laplace variable, and it is also supposed to be dependent on this flight speed, okay, as parameter. If this E is equal to E4 by 3, E2 and E1, what is the meaning of E2, E1, E3, and E4? Look, E1 is pre-multiplied by Q for obtaining here in the middle, the quantity key key vector. Remember that the key vector is a vector composed by key 1, key 2, key m like Milan, and this is the value of VB, V-body dot n in the first panel. So you have a panel in your undeformed configuration because you are you implemented a boundary element method, and this is the first panel, m equal to 1, and here you have V-body dot n, V-body depending on time, dot n depending on time, and this is the body point of view of the impermeability condition. This is the input for the aerodynamic in terms of the phi on the end. And so this vector is the input of our E2 matrix. We have defined this matrix. And this matrix E2, let me write here, the note already done. What we have already done? Already done linearized potential flow. And as a direct fruit of this linearization of the uncompressible potential flow, we have defined a E2 matrix which is capable to transform the key tilde vector, and I see this unsteady boundary condition evaluated for each panel, and through the definition of potential flow we have the value of the potential in the same panel. This is a vector. So when you apply E1 on key, you should have this key. Excuse me, whenever you apply E1 to Q model vector, you have key. When you apply E2 on key, you should have here the velocity potential vector. When you apply E3 on phi, what do you have? The E3 operator is another operator able to transform our potential flow into CP, pressure coefficient vector. The pressure coefficient vector is something similar to key vector, and is a vector defined on the body, giving the pressure value in the panel 1, transformed, the pressure value, the coefficient pressure value in the panel 2, and so on to the other. Finally, whenever you have the pressure distribution here, you are able, by using this E4 operator, to have the generalized force apart this constant, which is a multiplying constant. So at the moment we have analytically defined this operator. Next job is to define and identify all the other operators, the E1, E3, and E4, in order to build the final operator to be applied to Q tilde, identically like here in this reduced and analytic version, when we applied differential and transcendental operator. This C is a transcendental function of K for obtaining the generalized force in any time, for, in this case, for lift and moment with respect to the 1/4 chord. Okay, so this is our scope, our next scope. In particular, within the framework of this general theory, after evaluating this matrix here. Now I want to focus on this matrix, E3 at the moment. So evaluation of matrix transfer function operator E3 as a function of S eventually and as a function of U infinity. E3 by definition is operator able to transform the velocity potential into pressure coefficient vector in Laplace domain. So the theory beyond this matrix representation is the Bernoulli equation, of course. Okay, so in Bernoulli equation, we found that the time derivative of phi with respect to the time is equal to 1/2 the gradient of phi, which is the velocity, the square of the amplitude of this velocity is this, and plus 1 on rho pressure is equal to, is a function of time only, okay? It's not a function of space. This is the Bernoulli theorem, okay? And in particular, you can evaluate this quantity in the undisturbed flow, so at infinity here. And so we should have in this case, once here you have phi equal to 0 and any derivative of phi equal to 0, time, space, and so on, you have that here you have one on rho by p at infinity, for example. Okay, and this is the formulation of this theorem. Now, what this time derivative is representing? This time derivative is representing a derivative with respect to the time. This is an Eulerian derivative, which is performed with respect to the time, keeping x position constant. Okay. Now, the time derivative operator, as you know by flight dynamics course, is deeply depending on the frame of reference you are talking about, you are working on. Okay, and in particular, this time derivative is a time derivative in the air frame of reference. This is the air frame of reference. Air frame of reference. Which is fixed with the airport. And here you have your aircraft flying, and you have eventually a body frame of reference. Body frame of reference. This body frame of reference is actually sharing the x direction of the absolute air frame of reference, and this is typically zeta, and this is typically y in aeroelasticity, but this is a y in body frame of reference. This is an x in body frame of reference, and zeta frame of reference. And typically this flying reference system is moving with a constant velocity, which is equal to the aircraft velocity, of course. So here you have a velocity like this. This is flying. So how can I represent this airframe of reference derivative as a function of the body frame of reference derivative? What body frame of reference means? Body frame of reference means that you are fixing a point in this frame of reference, and you see what happens to the quantity with respect to the time, but you are moving, and here you are not moving. Okay. Please consider these two frame of reference with the coincident direction, x direction as x bar or x. Okay. So how can you consider this here, this time derivative? This time derivative means that you are fixing a point, fixed point in airframe of reference, and then take the time derivative. This is the meaning of this. Fix a point and take time derivative. And for example, here we are talking about the velocity potential. So fix this point and see what happens to velocity potential when as function varying time, keeping this point fixed, this point fixed. When you are here in this, this is me sitting on the aircraft, okay, and this is my new body frame of reference. In my body, when I take a time derivative in my body frame of reference, I consider a point in my time of reference, in my body frame of reference, okay? But now I am obliged to represent this physical concept. How can I describe this derivative in my frame of reference? Well, if you are like me here in this sitting on this wing aircraft, you see this point which is going in this direction far and far, moving with respect to me with the velocity u infinite, right? So when you are here in my side, you see this point going farthest and farthest and far in time, okay? And this point is moving with the velocity equal to u infinite. So if you want to perform this derivative, you have to follow this point with respect to u. So this time derivative is, in my side vision, as equal to the time derivative of phi with respect to time, but at x body frame of reference fixed, plus a convective term like equal to the velocity of this point with respect to me, which is I vector u infinite dot the gradient of phi. Okay, so this quantity in my reference is represented by this convective time derivative, in the sense that if I have to represent the variation of the phi quantity in a point which is moving with respect to me with a velocity like u infinite, you have to consider the time derivative in this point, in the time, plus this convective term representing the fact that this point is going with this velocity. Okay, so for this reason, this time derivative in hair frame of reference is equal to the time derivative in the body frame of reference. Remember, so keeping fixed the x body frame of reference point, plus what about the result of this is u infinite by the derivative of phi with respect to x, okay, which is a convective term. Important note that body frame of reference is the computational domain. Environment. Okay? So I'm interested to represent this derivative in this way. Let me do another comment. When you take the gradient of phi, you obtain the velocity of the fluid with respect to the absolute frame of reference. So the velocity you obtain when you take this derivative are velocity with respect to R frame of reference. And this is another point. Okay, what time is it? Okay, time for a break. I thank you. So a pause, 10 minutes pause for all of you. What about the connection today? It's okay?
Very good. Very good.
Ok. Mi state addormentare perché vedo che siete 8, quindi siete proprio scappati. Escaping people.
Guardi, veramente 27 siamo.
Io ci ho scritto 12 qua. No, aspettate, forse mi sto sbagliando. Ah, ok. Ok. Yes, 27. Ok, thank you. Let me have a coffee, please, because I skip everything today. Just 2 minutes. Thank you. Pronto? Sì, chi è? Ciao Angela, sto scendendo in questo momento, devo approfittare. Sì. Allora, vediamo. Sì, sì, guarda prima, quando è bene. Okay, here we are. At the moment, we have just represented this derivative, which is properly an air frame of reference time derivative, as a body frame of reference time derivative plus this convective terms, which is this here. So what happens to our Bernoulli equation? We have, after this position, that d phi on dt in body frame of reference, we will assume this from now on, and then we will not indicate this BFR in our representation, plus a convective term, df on dx, and we have this term and we have 1 on rho p minus equal to, excuse me, 1 on rho, the value of the pressure at infinite. So we can go ahead here and we can, let me represent this like phi dot plus u infinite. This dot is a time derivative in body frame of reference plus phi x. This phi x is representing the phi on the x plus this term, gradient of f, the amplitude to the power 2, plus pressure, and the pressure at infinite divided by rho. I don't know what happens. Okay, divided by rho. Now, if we want to linearize our Bernoulli theorem in this condition, we have just to discard this term. So we are considering a linearization. Okay, and after this linearization, we can define our CP coefficient like the jump of the pressure minus P infinite divided by the dynamic pressure. So a referent pressure like the dynamic pressure, which is 1/2 rho by U infinite to the power 2. If we consider this, we have the following. We have that P minus P infinite divided by this, you have that P minus P infinite divided by rho is equal to minus phi dot minus phi dot plus U phi x. Okay? And if we now multiply this by 1/2, and U infinite, to the power 2. We have that this quantity, the dynamic pressure, is just equal to -2 by U infinite multiplied by phi dot plus U infinite, the derivative of phi with respect to x. And this is the analytical relationship between the pressure coefficient and the velocity potential. Okay. Now we let me do a comment. A comment is what about in the steady state? In the steady state, the CP in the steady state is equal to minus, this is 1 to the, this is U to the power 2, this is -2 by 1 on U infinite dphi on dx. So in the potential theory, when you have a potential trend on an airfoil, and you have, for example, a typical value of phi is the following, and you have that the CP is something like the derivative of this quantity, and therefore you have something like that. It is the CP. Okay? But this is the unsteady case in general. And now let me undimensionalize this quantity. In a sense, I want to introduce, for example, the Laplace transform of this. We have that this CP field is in general a function of x and time. And therefore, when you take the Laplace transform, you have the CP Laplace transformed like a function of x and the Laplace variable s. And this is equal to -2 by U square infinite. Phi dot is s phi tilde, again function of x and s. And here we have U infinite, the derivative of phi tilde as a function of, again, of x of the point and the Laplace variable. Okay, so we'll take the Laplace transform, and now we can also to undimensionalize this quantity. In particular, we can introduce an undimensional velocity potential like phi bar equal to phi, the physical one. The velocity potential, the dimension of the velocity potential is the velocity by a length. And therefore, we can undimensionalize this, dividing the dimensional one by a reference velocity like U infinite, and by a length like, for example, the half chord, or the chord, for example, the half chord B. And so we can express the CP as -2. We can move this U infinite inside, and we have S by U. We can use one of this for put down to the physical, and we can multiply and divide this quantity by B, by the length reference, and this is the undimensional potential. And this U square is here, and so we have 1 on U infinite, and we have the derivative of phi, the physical phi, with respect to x. We can multiply and divide by this quantity by B, and B, and this is the undimensional potential, and this x by B is the undimensional x length, like x divided by B. And at the end of this, we have the formula -2 by what is this? This is a unique undimensional Laplace transform variable, like P. P is the undimensional. We have already introduced this variable last time. The undimensional Laplace variable. And so here we have 2 by P by phi bar tilde, the dimensional velocity potential, plus derivative of the undimensional velocity potential with respect to undimensional x value. And this is the very simplified and reduced form of the Bernoulli theorem, so expressing the pressure coefficient as a function of velocity potential here. But remember, we are interested on identifying a matrix relating the discretized phi vector with the discretized CP vector. Okay? Remember that these vectors are currently listing the component CP, the component of this discretized vector evaluated in the panel of our surface discretization of the body. These are the panel. What is it? Okay. We have divided the body into panel like this. And we have M panel. Okay. So we have to discretize this formula. And in particular, let's discretize in space at zeroth order formulation, which means that you are assuming that on the body the pressure coefficient are constant. In the panel here, for example, you have a unique value of CP, better the Laplace transform of the CP in this panel, like let me use the same quantity, like M. Okay, so you have in the M panel, you have CP M. Okay, and we have just to collocate this quantity. We're just to localize previous formula in xm point. So evaluate this formula in m point. Localize in m point. We have the following. We have Cp now in the m point in Laplace domain is equal to minus 2 p. Let me underline this p in color, p, and here you have the velocity potential evaluated in the same position like Cp, and so you have to use phi m here. Phi m to the panel m of the velocity potential, and now I have to perform this space derivative with respect to x. What does it mean? Here we have excuse me. What about a finite difference? In this point, we have to define, for example, the derivative of phi with respect to x evaluated at x equal to xm. In the finite element logic, you should consider this derivative here, just the difference between the derivative here minus the derivative here divided by this space interval. This is a very elementary way for doing this space derivative. So we have phi in m plus 1 minus phi in m minus 1 divided by 2 delta x, for example, 2 delta x. And this is the x-axis, as you know. Okay, and when you collect this, all this space derivative on your domain, at the end of the story, you will define a matrix like D, M, N, applied to phi N, and from 1 to capital M. And this D matrix is the matrix enabling you to give you the value of the derivative in this point here by plus, this is a diagonal term, 0, 0 diagonal term, and here you have, look to this definition. So you have here 1 on 2 delta x in this position, and minus 1 on 2 delta x in upper diagonal position. And here you have lower and upper diagonal as applied to phi 1, phi 2, bar tilde, to phi bar tilde m. When you do this multiplication to obtain the phi on the x in the first point, that next in the second point, and all the other. Okay, so I have the possibility by a finite different logic, for example, I can express this space derivative in this way. And ladies and gentlemen, I'm finished because I'm saying that the CP in Laplace domain is the CP distribution R is equal to minus 2. This is the undimensional Laplace variable P by, here we have this M index, which is equal to this M index, excuse me, I have M here, and therefore I can write this in this way, like delta Mn phi bar tilde n, and this is identical to this. This is just a generalization, like a multiplication for a identity matrix, plus summation of n, like nipple from 1 to m, d mn phi bar n again, and therefore we have, here I am summing in n quantity, I have minus 2 summation n quantity from 1 to capital M of delta mn by p. Delta is Kronecker delta function. Yes, Kronecker delta function. Red color p plus d mn as applied to phi bar tilde. By n. And so this here no, I lost my page. Ah. No. Okay. CP is equal to minus 2 P delta M N plus D M N phi okay, and therefore this quantity is exactly the E3 matrix M enter, which is a function of P. Okay, so this is the Bernoulli operator is 2. Okay, so this operator again is a function of the n-dimensional Laplace variable, or is a function of S and U infinite. Okay, and as you can see clearly, this partial E3 operator is a linear function of P. You have P to the power 1, so it's proportional at P. Okay, and this is the operator relating the velocity potential and CP. Okay, please emphasize This is valid, do not forget, for uncompressible, unsteady potential flow. Okay? Okay. So, at this point, we have filled and considered and completed the description of this operator. Remember that we have completely represented the E2 operator, and I remind you that this operator is depending on S or P by and transcendental function, and then we have a potential flow operator, we have Bernoulli theorem operator, which is the E3 and which is a linear function of the S variable. Okay, now we have to complete our vision describing this E1 vector and this E4 vector. Okay, I want to discuss with you to this E4, which is easier, and then I want to leave E1 as the last described operator for complete our description of our acidic dynamic matrix. So E4 is the E4 operator is an operator transforming the CP vector into generalized aerodynamic force vector, E vector. Okay? For example, in Laplace domain. Okay. In order to define this operator, we can easily remind that the n generalized force in Laplace domain is equal by definition to the projection on the force per unit surface on the boundary, for example, given by the force given by the steady aerodynamic. Imagine to have this force analytically as a T vector, which are Newton on square meters Pascal, dot we have to project onto psi and modal vector. Okay, so this is the definition, and on the basis of the definition we have that this vector and this force are okay. Start with the time domain, it's not a problem. In time domain, no problem. We have a function of time, we have a function of time, and therefore this generalized force is equal to T for unviscous flow is minus P by N. And so we have minus the projection on the body of Pn dot psi n. Yes. Okay. But P, the pressure, is equal to the pressure at the infinite plus dynamic pressure by the Cp vector. Okay, this is by the definition of Cp. And therefore, P can be expressed in this way. And therefore, the generalized force in time is equal to minus the integral of P infinite n dot no, 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 no. I cannot support this. Oh, okay, okay. So this minus 1/2 rho u infinite to the power 2 integral of Cp. Cp should be in general a function of x, surface, and time. We should have an unsteady varying Cp field in my body. And we have the normal n dot psi n. Okay, in the x, in the s. Now, see what this quantity, see this quantity? P is a constant, so this quantity is P by the integral of n dot psi n ds. This is equal to P infinite Gauss theorem. We have the dot product with a normal, so this formula is a strange quantity. This is the volume integral on the body of the gradient of C. The divergence, excuse me, the divergence of C. Divergence of Cn ds. Okay, so what is the divergence of C? It's something related to the capability of C to expand or compress. And this quantity is 0 if the mode shape is not representing an expansion of the body. But typically, when you have a mode shape, you have something like this. So you are not representing typically the expansion of the so-called breathing mode, mode di respiro. But you are currently representing mode such that in one phase of the surface of the mode shape, you have the same displacement as in the other opposite phase. Okay, and so this term is typically going to 0. And therefore, the only contribution to the generalized force in time is dynamic pressure and then we have the integral in the body surface of minus Cp x time n dot psi n. Okay, and this is the final formula relating the generalized force, and the pressure coefficient. If you typically localize this formula, I mean, if you assume that the pressure distribution, as before, is constant in each panel, this integral becomes a summation on the M, like Milan, panel on your body. And so localizing, you have that the nth generalized force is equal to dynamic pressure. And here you have summation. You have this integral to be performed like a summation of summation from M going to 1, from 1 to capital M. And we have the integral on the single surface M of N dot psi M, like Milan, ds, and then multiplied by Cp in the point M, like Milan. Okay, and therefore we have this apart a minus sign. I have a minus sign here, this minus sign. We have a term, this term here, which is depending on E, which can be defined like a matrix, formally an E4 matrix, which is N and M defined. You see N like Naples here. I'm sorry, I have N here. Because I am projecting on the N like Naples mode, and I am evaluating the pressure coefficient locally in the nth panel, okay? So obtaining the CPM. So this expression is giving us this quantity as equal to 1/2 rho u infinity to the power 2 summation E element, E4 element, and M for M going to 1 from 1 to capital M by Cp in Laplace in time domain as a function of index M. Okay, and this relationship is in time domain because this coefficient are time depending. However, we can define this relationship in Fourier domain or Laplace domain better by considering this symbol. This is time depending, this is time depending, and this is the matrix E4. This is the matrix E4 and M. Is mainly representing this inner product between the local unit normal and the value on a panel of the mode shape. So, for example, in this panel here, you have a normal like this. This is the normal in the panel N, and here you have the value of the displacement of the mode. This is the value, for example, of the displacement. This is the value of the displacement of the N mode like Naples evaluated at the M like Milan panel. And it is exactly this quantity here. So you have to consider this scalar product and make the integral of this scalar product inside this panel. And this is the coefficient E4 and M. This is essentially a mode projection coefficient, actually projecting the mode shape, actually projecting the mode shape value on the normal of the surface. Okay. And so we have obtained easily this operator in Laplace domain. We don't have the time dependency, and we have just this definition for E, for and M. And therefore, at the moment, we have actually defined three, excuse me, of the four operator. We have defined E4, we have defined E3, and we have defined E2. E4 is not depending on S, not depending on S, whereas E3 is depending on S in this way. This is P, which is equal to SB by U infinite, and E2 is also depending on S through the delay mechanism related to the wake convection. We have only to define the last operator, transforming our model coordinate into the normal wash in each body panel. And after this definition, we have a clear and complete description of our unsteady aerodynamic matrix, giving us the generalized force as depending on the motion. Okay? And I finished. I thank you for your attention and see you.
Professore, mi scusi, ma perché E4 non dipende da S? Cioè CP non dipende dal tempo? Quando facciamo la trasformata di Laplace non dovrebbe venire...
Allora, prima cosa dovrebbe parlare in inglese, primo. Seconda cosa, this is E4 and this is CP at two distinct values. So when I have defined this coefficient multiplying CP. I have not included the CP inside the definition of E4. Okay? So in the definition of E4, you have to perform a space integral on the panel of the quantity n dot psi, and the normal dot product with the component of the mode shape here in this point. Take this scalar product. Okay, this scalar product is a function of the point in this surface, and so take the integral on the surface of this point, and you have the term E4 and M of this matrix. So when you combine this matrix with the CP value, then in this way, summing in M, summation, then you have E tilde N. Okay?
Sì.
Ok? Sì?
Questa domanda, diciamo, è di carattere amministrativo. Mica gentilmente mi potrebbe dire la data dell'appello di febbraio?
No, adesso non gliela dico perché devo fare un'altra... Adesso, aspetta, prima cosa è tutto pubblicato. Tutto pubblicato.
Sì, no, era solo per non mandarle una mail, approfittavo della...
Non devi mandarmi una mail, devi andare su InfoSud e trovare la data degli appelli, che c'è tutti quanti
Ma al
scritti.
momento non posso vederla, al momento non posso vederla.
E perché, scusi? Tutti gli studenti le possono vedere.
Perché non ancora faccio i 3 esami per passare al secondo anno.
Lei non può fare aeroelasticità se non fa gli altri esami,
Sì, però io ho ancora gennaio.
Vabbè, mi scusi, posso finire un attimino per tutti quanti questa cosa? Ok. Ok. And so, E4 does not depend on CP at all. E4 by CP is giving you E. E3 by phi is giving you CP. E2 by Q is giving you phi. And finally, E1 by Q is giving you Q, as we see in the next lesson. After this, I would like to organize with you a recovery lesson for this Tuesday, or excuse me, for this Wednesday. I remember that you are free on Wednesday, typically, So my proposal is to have a recovery lesson next Wednesday from 8:30 up to 10. It's okay? However, I will send you an email on this issue. And if there is anybody not in agreement with this, please tell me. Okay?
Professore, avremo il venerdì il corso di Experimental Aerodynamics.
Not Friday. I'm talking about Tuesday. Wednesday.
Okay.
Wednesday 8:30. Wednesday 8:30.
Okay, sorry.
Okay. Okay. And so, any other questions? Okay. So if there are no questions,
Professore,
yeah.
La faccio in inglese sulla sezione tipica. If we consider just a steady model for the aerodynamics, does it make sense to do a flutter analysis?
No. The only stability analysis that makes sense considering a steady operator is the divergence, if any. If you want only to study divergence, as the divergence is a critical condition occurring at zero frequency, at 0 poles, if any, 0 poles, therefore you have to evaluate all the operator for Laplace variable equal to 0. And if you evaluate the unsteady aerodynamic for S variable or K variable equal to 0, you will have only the contribution of the steady term. The steady term of structural dynamic is the stiffness, because in that case, in structural dynamic model, for S equals 0, you are currently cancelling the inertial contribution. And therefore, you have only the stiffness matrix K. You have cancelled the S squared by M term. Okay? In the identical way, if you want the steady part of your unsteady aerodynamic operator, you have just to put S equals 0 in your unsteady aerodynamic. And if you do that, you will obtain the steady operator for the aerodynamic. And this is the active operator for giving you eventual 0 pole, which is the divergence condition. Okay?
Okay.
Almost. But we will clarify this point. Do not worry. We have time to clarify this.
Okay. Thanks. Good
Okay.
afternoon.
Any other question?
Professore, scusi. Senta, volevo chiedere una cosa, ma le esercitazioni vanno fatte, cioè dobbiamo scriverle in inglese o vanno bene anche in italiano?
Come volete.
Perfetto, grazie.
Prego.